The content in this presentation is covered on pages 97 through 99 of your textbook, and it's meant to help you achieve learning objective number 20, which is to write a generalization relating air temperature and the amount of water vapor needed to saturate air. Be sure to skim these pages before watching the video and read the chapter carefully before attempting the quizzes. Humidity is the general term used to describe the amount of water vapor in the air. Water vapor constitutes only a small fraction of the atmosphere, varying from as little as 0.1% up to about 4% by volume. But the importance of water in the air is much greater than those small percentages indicate. In fact, water vapor is the most important gas in the atmosphere when it comes to atmospheric process. Meteorologists use 5 methods to express the water vapor content of the air, including the 2 shown here, which are absolute humidity and the mixing ratio. These 2 numbers are similar in that both are expressed as an amount of water vapor contained in a specific volume of air. The absolute humidity is equal to the mass of water vapor in some volume of air divided by the total volume of air in cubic meters. So the dimensions for this value are grams per cubic meter, which is a density. Absolute humidity is not, however, the same thing as the density of air. It's only that part of the total density that's attributable to water in its gaseous state. So it doesn't include the mass of any other molecules besides H2O, and it doesn't include the mass of any liquid water. As air moves from one place to another, changes in pressure and temperature cause changes in its volume. And when those volumetric changes occur, the absolute humidity also changes, even if no water vapor is added or removed. Consequently, it's difficult to monitor the water vapor content of a moving mass of air when using the absolute humidity index. So usually meteorologists prefer to use the mixing ratio to express the water vapor content. The mixing ratio is the mass of water vapor in a volume of air divided by mass of everything else besides water. Because the mixing ratio has only units of mass in both the numerator, the upstairs number, and the denominator, the downstairs number, it doesn't have any dimensions. It is in fact a dimensionless number because the upstairs mass and the downstairs mass cancel each other out. Because it's measured only in units of mass, the mixing ratio isn't affected by changes in pressure or temperature. So the figure in this slide can be used to illustrate absolute humidity and mixing ratio in an imaginary balloon as it rises in the atmosphere. Near the surface, we can see that the balloon is known to be 1 cubic meter in volume, that it weighs 1 kilogram, and that 20 grams of its total mass is water molecules in their gaseous state. We can calculate the absolute humidity at the surface by dividing the 20 grams from the mass of the water vapor by 1 cubic meter, which is the volume of the balloon, to get 20 grams per cubic meter. That's easy enough, right? We can also determine the mixing ratio at the surface by dividing the same number, 20 grams of water vapor, by the total mass of the balloon, which is 1 kilogram. And in this case, we get 20 grams per kilogram. Or if you want the dimensionless version of that number, it's 0.02 on your calculator. Okay, now let the balloon go and watch what happens as it rises in the atmosphere until it doubles its volume. Under these conditions, we can see that the balloon is now 2 cubic meters in volume, that it still weighs 1 kilogram, and that it still contains 20 grams of water vapor. When we can calculate absolute humidity under these calculations, we divide the 20 grams of water vapor by the new balloon volume, which is 2 cubic meters, and now we get 10 grams per cubic meter. So the absolute humidity is half of what it was at the surface. How about the mixing ratio? Is it different? No. No molecules have left the balloon, so we still have a mixing ratio of 20 grams per kilogram. So the absolute humidity will decrease as the parcel rises and the volume increases, but the mixing ratio remains constant. Pretty neat, right? The problem that both of these numbers have is that the mass of water is difficult to measure. And that's why we don't usually see these numbers in weather reports. Relative humidity and dew point are easier to determine, and we'll figure those out in the next presentation. But before we do that, I want to talk a little bit about vapor pressure here, and we'll do an imaginary, a thought experiment here. If we imagine ourselves in a laboratory, we can get vapor pressure or relative or absolute humidity and moisture content using closed tanks with thermometers and pressure gauges. So we can determine the moisture content of the air from the pressure exerted by the water vapor. So to understand how water vapor exerts pressure, imagine one of these closed tanks, and inside the tank is nothing but pure water and dry air at 20 degrees C. If you leave that system alone, almost immediately, some of the water molecules will begin to leave the water surface by evaporating into the dry air. Initially, many more molecules will be leaving the water surface, evaporating, than will be returning to it, or condensing. The addition of water vapor into the air can be detected by a small increase in pressure. And that increase in pressure is a result of the motion of the water vapor molecules that were added to the air through evaporation. In the atmosphere, that pressure is called vapor pressure, and it's defined as the part of the total atmospheric pressure attributable to water vapor. Over time, as more molecules evaporate from the water surface, the steadily increasing vapor pressure in the air above will force more water molecules to return to the liquid until eventually a balance is reached, in which the number of water molecules returning to the surface equals the number leaving. At that point, the air is said to have reached an equilibrium called saturation. When air is saturated, the pressure exerted by the motion of the water vapor molecules is called the saturation vapor pressure. So in a separate experiment, we could take the apparatus that's shown here, where the air is saturated, in other words, evaporation and condensation are equal, and add heat. So what happens to the state of equilibrium that we had in the last slide once we turn the Bunsen burner on? It's gone. It's been disrupted. The extra thermal energy increases the rate of evaporation, which causes the vapor pressure in the air above to increase. So the vapor pressure will continue to increase until a new stasis, a new equilibrium is reached, until that air gets saturated. So based on the last experiment, we can conclude that the saturation vapor pressure is temperature dependent. And that's really a very verbose way of saying that at higher temperatures, it takes more water vapor to saturate the air. And that's actually even a complex way of saying the third thing, which is warm air is able to hold more moisture than cold air. If we repeated that, the last experiment where we added the heat to the closed container, and we did that and heated those systems up to a range of different temperatures, and wrote down the value from the pressure gauge when we saw the equilibrium reached, we would end up with a table of data like the one shown here. So this table shows the amount of water vapor needed to saturate 1 kilogram of dry air at a range of different temperatures. And you can see from looking at this data that for every 10 degrees C increase in temperature, the amount of water vapor needed for saturation almost doubles. So roughly 4 times more water vapor is needed to saturate 30 degrees C air than is needed to saturate 10 degrees C air. So 4 times as much water vapor is required for warm air, 85 degrees Fahrenheit or so, than for air at about 50 degrees Fahrenheit. The atmosphere behaves in just about the same way as the closed container, but in nature we have gravity preventing the water from escaping rather than a lid. Also, as with the container experiment, water molecules are constantly evaporating from any liquid surface. So that means not only lakes and oceans, but also cloud droplets. Constantly evaporating even from the smallest little bodies of water. And at the same time, other water vapor molecules are condensing back to a liquid. And the main difference between doing this in the laboratory and seeing it happen in the real world is that in the real world, we don't always reach a balance. More often than not, more water molecules leave the surface of the water, lakes, oceans, puddles, cloud drops, than are arriving. That's called net evaporation. An exception to this is when we are forming fog. So as you watch fog banks form, more water molecules are condensing to liquid than are evaporating from the tiny droplets in the air. That's net condensation. So what determines whether the rate of evaporation exceeds the rate of condensation, or vice versa? One of the major factors is the temperature of the water, which determines how much motion the water molecules possess. So it's kinetic energy. At higher temperatures, the molecules have more energy and can more readily escape the surface of the water. Vapor pressure is the other major factor that determines whether evaporation or condensation is dominant. So remember from our closed container example that vapor pressure influences the rate at which the water molecules leave or evaporate. But it also affects the rate at which they return to the water surface or condense. So when the air is dry and we have a low vapor pressure, the rate at which water molecules escape from the liquid surface is high. As the vapor pressure increases, the rate at which water vapor returns to the liquid phase also increases. So use the content provided on the Canvas site, as well as the textbook and other outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape for the midterm. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.